Welcome, everyone. So the timer says it's time to go, so let's go. Welcome to this talk titled Data Consistency, Analyze, Understand, and Decide. I hope you had a great lunch, even though it makes it a bit harder for me to keep you all awake, but we'll see. So who am I? My name is Jacomet at Jacomet on Twitter. I'm a principal software engineer at Software AG Terracotta. We do all of these in the open source world. So that's Ehcache, Quartz, and Terracotta. Closer to my 40s, I'm still a developer at heart, even though I could not dodge fully all the management things. Wide interests from concurrency to API design, and anything that can bring me new knowledge. Really, learning is a thing I love. And I'm also part of the Devoxx family as a program member for Belgium. So keep the talks coming for the next Devoxx. Why this talk? Well, I've been presenting on caching for a while now, and usually the focus when I do present on caching is performance gains, which is one of the main reasons you end up doing caching. Ease of use. We try to do a caching that, like Ehcache tries to be a caching library that is easy to use. The integration points, Hibernate, Spring, and others. But I at least remain mostly silent on the consistency issue that can crop up in your application as soon as you move from a system without caching to a system with caching. And not only that, but also, distributed systems are becoming the norm rather than the exception. Even though most of you probably don't have the same problems that the Twitters and Facebook, you're still trying to grow your systems and make them more and more available to more and more users concurrently. And you can do that with or without microservices, but that's also something that has an impact, like distributed system and microservices, on the whole consistency debate. And let's be honest, we all have some kind of marketing associated to what we do, and that makes some of the tools we're offered as developers a lot of times sound like magic. And it may make up for hard wake-up calls. When the problem happens in production, you start losing either customers on your website or transactions from what your customers are doing, or duplicate transaction or anything like that. It's like, oh, what's happening? And we all know that we should build on the shoulder of giants. There is no need to code every single application in some assembly language. We're all using higher level tools, be it the JVM, the Java language on top of it, or any of the other languages, and even on top of that, frameworks and databases and NoSQL stores and everything like that. But it's not because you're building on top of that that it shouldn't look inside. My interest in concurrency stems from such a story. When I was a developer in a big bank working on a dealing room application that we developed a fat client using Swing, in development, everything was just working fine. We had machines working fine. The moment we delivered that application to the first traders, it deadlocked, like 2 minutes after starting. The problem came from the fact that at that time, developers, like multi-core machines, were not the norm for developers. And while the machines we had were hyper-threading enabled, it was actually BIOS disabled by the IT department for fear of impacting their package automatic installs and stuff like that. While on the other end, the traders had multi-core machines, multi-screens, all kind of things that have an impact on that Swing application. And while the team was a team of junior to experienced developers, I was considering myself a junior back then, 4 years of experience, so not the traditional senior consultant, but still. And the only thing nobody had was a real experience with the Swing threading model and what it meant. And so the way we fixed it was by looking inside, understand how it works, start reading stuff about that, because when you look, you actually find some of that documentation, and then make the application work. And then we had lots of fun, and we managed to do very smart things building on top of that. So it was really an eye-opener for me, and moved me from simply being a user to being someone who, while I love building on top of others' work, I also need to understand the way it works and why it works. So, quick agenda. If we talk consistency, we'll have to talk consistency as in ACID. We'll have to talk consistency as in the CAP theorem, because these are actually two different definitions. But then we'll also have to look at what exactly does that mean for an application. The goal here is not to give you all-made answers for your application, because I don't know your applications. So the goal here for me is really to make you aware of what you're building on top of, and then you can understand what are the trade-offs you're making and how they can impact your application, your business. But first, consistency. I mean, IT loves overloaded terms. So it's going to be a term, and between the title, probably, the consistency in ACID and the consistency in CAP, it already has 3 definitions. So first of all, let's move back to just a word. And when you define a model with a set of rules, if you are consistent within that model, it means you are respecting the rules. And we'll see that it's the whole definition of the rule set that really gives the specific meaning to consistency. A few examples. Serial execution in a program thread. We all know when we code on the JVM that int x equals 5, print x should print 5. The thing is, as soon as your single-threaded program becomes more complicated, you need to be aware that the platform you're building on today, the hardware, doesn't have to respect that rule. It can execute the operations in any order as long as you cannot perceive that it cheated. And it's cheating for good reason. It's cheating to be faster. So that's already something. Even then, you've got a set of rules, but yeah, internally, they can be not respected. I mean, they cannot be visibly not respected, but internally, they can be optimized to work better. The Java memory model is another good example. So Java 5 started with the introduction of its Java memory model, and that is a very strict set of rules with regards to visibility across threads in a concurrent environment. Well, I can tell from experience that when you do not respect these, sometimes it works. And then at one point, it stops working. And the reason it stops working is because probably the JVM, when it is not too much loaded, has time to give you these guarantees, even if you did not ask for them. But when you start loading your system, it no longer has that time. And it says, oh, I can go faster if I forgo all of these because they're not being asked. Let me go faster. And suddenly, all hell breaks loose. So we see that in that context, consistency is really about that. A model, set of rules, and you're consistent if you manage to respect these rules. So let's move to the ACID side of things. So from the database world, consistency means that the state of the data respects a set of constraints, all the constraints you've placed upon it. The foreign key, the constraints between columns, the triggers, everything. And when you save state in the database can only accept that state if it is consistent with this set of rules. Which means also that already, depending on how many rules you place upon your schema, the consistency can be different. I'm going to skip over the A and the D today. That's not the point of the talk. A for atomic and D for durable. But we need to talk about isolation. So as soon as you want your database to actually perform more than one transaction at a time, you need to define not only consistency, but also isolation. And isolation tells you, in its stronger form, that all the operations you're doing in parallel can be represented as if they happened one after another. Well, this is cool, but we all know that if you have to serialize all your operations, you're slow. There is no other way around that. You need to parallelize some of them in order to be faster. And all in all, the NZ SQL defines 4 levels of isolation, and the reason you've got 4 levels is because you've got 3 identified read phenomena that the levels protect you against. And of course, consistency and isolation are related. They're closely knit together, and usually they're where you can actually do some configuration and play a little bit with the rules with regards to what your application is doing with the database. So a quick look. I hope this is mostly a reminder, but otherwise it's worth understanding all of that as soon as you work with the database. Isolation level on the left go from less isolation to more isolation, so faster to slower. And you've got the three different phenomena listed on top, and you see that indeed you must be serializable so that you have no read phenomena possible with your data. And what does that mean? Well, we all, or at least most of us, should be Java developers, given the focus of the conference. Usually what you can do is you can configure that in your data source. Like the connection to the database will have an isolation level associated with it. Frameworks may offer you some configuration. So if, for example, if you use Hibernate and you let Hibernate create the data source for you, then you can configure that from the Hibernate configuration. Of course, you'll often want multiple isolation levels, depending on what you do. But when you pool the connections, you can really have one. And so if you want to use these multiple pools, these multiple levels, you end up using multiple pools. And for example, Spring Framework provides nice abstractions where you can define multiple data source and then an aggregate data source, which will do the selection based on the isolation level you declare at the transaction level. So you move really the abstraction where it belongs instead of being stuck with the way it ended up being implemented. But I've been using Hibernate as an example. So Hibernate is a popular ORM framework, knows what to do with your database, but as soon as you try to enable caching, it starts asking you even more questions, like, what kind of strategy do you want for caching? Why is that? Well, it's because what I said. If you're just relying on the database, you get what the database is configured to give you. A given isolation level, consistency according to the schema rules, all that kind of thing. But as soon as you move a cache in front of that, well, a cache is what? It's a glorified hash map in memory. I do some caching, so it's more than that, but from you users, that's what it is, with eviction and expiry as the main characteristics with regards to how entries behave. And so you need strategies, and when seeing them, you'll understand why. So the first one is read-only. There you plainly say to Hibernate, you know what? My data is immutable. So either it exists, and you can cache it forever, or it doesn't exist, and when it gets created, you can cache it forever. And if I try to do an update, well, this should blow up. You've got non-strict read-write. I'll dive a bit more on that one later. We've got read-write, and then we've got transactional. Well, transactional might sound like a good idea because then you gain back all the guarantees that the database gives you, except that you moved from a single transactional resource to multiple resource, which means you've crossed over into the world of distributed transactions. And you're suddenly, again, in a different world with regards to how your application will behave and what will happen when things go well or when things go wrong. Going back to the different read-write strategies, non-strict read-write, well, its name comes from the fact that you actually open a window of inconsistency. Because in order to update the cache, what the transaction will do is that in some cases it will invalidate the cache entry before committing and invalidate it after, trying to make sure that no one else can get in the cache and see an outdated value. The problem is that a concurrent transaction, given there is no locking or exclusion in place, could very well go to the database, find the old value because you have the proper isolation level, bring it back at the application level, and install it back in the cache. And it will stick there for the duration of the commit. Well, commit could be instantaneous, but even when they're instantaneous, it is just a factor of the level of concurrency in your application, because that instant under load could become much longer. And so yeah, that's what I just explained. So in order to protect against that, without going fully transactional, you've got the read-write strategy, which resolve inconsistencies by using soft locks. A cached item can only be read by a transaction that's been started after that cache item's timestamp. And it means that if you're an older transaction and you need access to that data, you will do a cache miss. Well, there is effectively a value in the cache, but the cache will tell you, no, there is no value. I mean, the wrapper Hibernate will do that for you. And when an entry gets invalidated, it's not removed. There is a tombstone in place that also has a timestamp. And that makes sure that nobody can replace that tombstone unless it is a transaction, a later transaction than the one that installed the tombstone. And this is the kind of things I mean when I want to promote awareness of data consistency, because this is very easy to turn on. Hibernate caching is a flag in the config, and the rest is provided by the framework. But as an application developer, you need to understand what it means for what happens from now on. And this is not even the whole story. Because in the world of database, research continues. I'm not a researcher myself. I'm more of a product developer, but I try to read stuff once in a while. And they've identified more phenomena, and thus defined more isolation levels. And so, for example, you can have read or write skew phenomena, and they've added snapshot or cursor stability isolation levels. So just to give you an idea, we're going to have a quick look at, and these were examples. You've got others. And will there be even more later? Well, that's the whole point of research, maybe, because this is the problem. It's a hard thing to define. So here, if we look at what a read skew is, you've got two register variables, whatever, and what you try to do is maintain them such that their sum is always 100. And you've got two parallel transactions. The first transaction starts reading and reads X and sees that it's 50. That's fine. But then you've got another transaction that decides to change a little bit the balance while respecting the invariant, and which moves X to be 25 by doing a write, and then Y to be 75. And then it commits. The problem is that the other transaction still hasn't read Y, and when it finally does, it sees the value 75. So now you've got two variables that have 125. By the way, classical question when you start discovering database, why the heck do I need a transaction for reads? For that kind of stuff. Otherwise, you're open to that kind of stuff if you decide to read outside of any transactional context. The write skew works a bit the same. Here, we're trying to preserve that the sum of them should be below 100. And first transaction reads X, then the second transaction reads Y, and they both decide that they can update the other value depending on the value they saw by making sure they respect the invariant. And so you've got the first transaction saying, oh, X was 30, I'm going to make Y 60. 90 becomes the sum, we're fine. The problem is the other transaction saw 10 on Y. And so when it decides to update X to 50, it does not realize that it's actually breaking the things. And you see the two commits at the end. Well, the isolation level will determine what happens. That's really what we mean. So that's one side of the world. But also, the whole space has evolved. I mean, and it's not recent. Like Brewer's conjecture is a keynote in 2000. The cap theorem is a few years later. But so, in order to understand that, we need to have a look at definitions of what the C, A, and P mean. And I'm going to start with A, because I want to, when we talk about C, go in depth about it. So, what does availability mean? Availability really means that all the requests going to a non-dead node must complete successfully. Waiting forever, it's not completion. Returning a message that says cannot answer is not successful completion. So that's really what availability means. And this is very strong. I took the definition from the blog Aether, the guy who does JSPN. If you've not heard of that and you're looking into the NoSQL space, you must have a look at what he does. It's really, really interesting. Moving on to partition, which is partition tolerance. And in reality, what this says is that if you're partition tolerant, you can do something when a partition happens. And since we know that in distributed systems, partition will happen, it's no longer an option. Your system wants to be partition tolerant. You need to be aware that this will happen, and you need to understand how it's going to react when that happens. Will you forfeit consistency? Will you forfeit availability? That's up to you, but you need to do something. And partition is not just a network property, because when a node doesn't answer, you've got no idea if it's the network that's dead. By the way, is the network dead on the request going in or the response coming back? You just don't know. It could be that the network is just perfectly fine, but that other VM is in long GC for dozens of seconds. And so from the requester, there is no way to differentiate between that. So moving back now to consistency, which is really atomic consistency. And in the context of the CAP theorem, it really means linearizability and linearizable registers. So not only is the word hard to say, and I practice a bit because otherwise I keep forgetting how to say it in English, but also what the heck does it mean? So let's go back to consistency, the term, not the definition. You remember what I said? It defines a model with a set of rules, and being consistent means the rules are respected. So in order to define linearizability, gosh, I knew I would do that, we need to understand exactly what we mean with regards to the operations. First of all, no operation is instantaneous. They all take some time between the moment you ask for the operation and the moment the operation finishes. If you're looking at a synchronous programming model, it's the moment you invoke that method and the moment you get control back from the invoked method. If you're looking at an asynchronous model, it could be even longer because it's the moment you send your message and it's the moment you can finally react on that promise, future, or whatever you got when you send that message. Luckily, we know that the time is finite. Because if the time is infinite, then you actually don't have an operation. It means it's stuck somewhere. And so it goes from the beginning to the end of the operation. That's the time span. However, the effect of the operation could be visible at any time during that time span. And if we pick one point in time during that span, and we say this is the moment the operation becomes visible, we can call that point the linearization point. And it's with that point that we can finally go back and define linearizability. If there is a valid sequential history of operations using their linearization point, then you've achieved linearizability. Knowing that you cannot swap the order of an answer and an invocation. If an answer came before an invocation, you cannot swap that order. Graphics are better than words, especially for that. I lifted that example from Wikipedia. Here you see, this is what you observed as an outside person. You saw A invoking lock, B invoking lock, then A fails to lock, B gets the lock. That sounds invalid. This is not the way you would naturally assume a lock behaves. So maybe we can reorder it that way. A invokes lock, A fails to lock, then B invokes the lock, and B succeeds to lock. But that's strictly invalid. It does not respect the semantic of a lock itself. So again, linearizability of the operation must respect the set of rules. This is not how a lock behaves. If you cannot acquire the lock, nothing else happens to the lock, then another one cannot acquire the lock. But you can again look at the order slightly differently, and since no answer arrived before an invocation, you can actually move all the B actions at the beginning by saying, oh, it must be that actually B invoked the lock first, got the lock, then A invoked the lock, and A failed to lock. Remember, you've grouped, in order to do that reordering, you've grouped them on that imaginary instant. So yes, if you're observing the system from the outside, it's very well possible that you called A.lock before B.lock. But in the end, what you got was that. Somewhere between the stack, it raced and B won. What does that mean in practice? This sounds pretty complicated. Well, first of all, it has powerful consequences, because it means that the completed operation must be made visible, which is good, because if you remember, when you're doing concurrent programming, most often the problem you have is you're missing that update from a concurrent thread. It also means that stale and non-monotonic reads are prohibited, meaning that once an operation has completed, you cannot see a previous value, and also you cannot jump to a previous value at a later point in time. You will always see the value incrementing. You may miss some reads, because if writes happen really close to one another, your read operation could skip a few writes, but you will not see them out of order. And also, it is a stackable model. And it is the way a lot of things are built. Like, your CPU compare and swap operations have that property. And it's on top of that you end up being able to build the whole Java util concurrent thing. And then on top of that, you know that you can build stronger or more user-facing constructs. And so I think the main consequences of the CAP theorem was that, first of all, it attracted attention to weaker consistency models, because the linearizability we just defined is really, really strict. And people were fighting, saying, no, but it's not true. I can be consistent and available and partitioned. Look, my system does it. But the research has shown that really what it means is your C prime, A prime, P. You've done something to the definition of consistent or available to enable to have these variations together. Again, I took that from Efir blog post on the different strong consistency models. What this means is that everything you see in that pink on my screen, purple there it seems, is really the space in which you can't have availability if you want that consistency level. It's been proven all these different strong serializable, linearizable, sequential, serializable, and others, you can't. There is no way you can be available in the face of partition and keep that consistency guarantee. In the blue on the left, here you find a place where you can actually keep pretty strong consistency guarantees as long as you relax a little bit the availability. And the relaxing you need to do is you need to say, once a client talks to one node in my cluster, it will keep talking to that node. And if it's that node that fails, well, too bad. That client will experience unavailability, but the rest can still work. And in that world, you've got causal consistency, where the idea is that you create this chain of events that make sense as long as you can declare that an event depends on another one. Think a bit like what would happen if, when reading a Twitter stream, you would see an answer to a tweet before the tweet itself. Or like you see that it's an answer, but when you try to look up the tweet it answers, you see nothing. That feels wrong. And that's the kind of stuff that causal consistency gives you by providing such guarantees. And then the green space is the space where you keep strict availability, but of course you've got way, way lower consistency guarantees. this is the space where most NoSQL, NewSQL database strive, and even caching solution, because they'll try to sell you, my consistency is better than your consistency. And what's really important is to understand that most often the marketing terms that are used don't necessarily have a very strict definition. Abuse of terms. I mean, we all do it. Ehcache with Terracotta does it. This is what we call strong consistency. You've got a cache operation, it goes to the Terracotta client, goes to the Terracotta server, but of course, you're not the only client. There are other clients, and the problem is the clients could have the same mapping in their near cache, and so you need to invalidate them. Well, if you want strong consistency, meaning that all clients, once the operation has returned on the client who initiated it, to only see that new value, you need to wait. You need to wait for the invalidation to be completed. And only once the invalidation are completed, then you can return, give back control to the client, and tell it, yep, it's done. I've put my thing in the cache. Well, you realize that the latency, I mean, that strong consistency comes with a price. It increases the latency of the whole operation. On the opposite, we have a mode that we call eventual consistency, which when you read the literature is more like sequential consistency, where when you talk to the cache, it talks to the client, talks to the server still needs to tell the others to invalidate, but you do not wait. You return immediately. And the invalidation confirmation comes at a later point, while you can still make progress with the global operation. And so that's why it's really important to understand what these terms mean and what exactly you're buying with that React, Cassandra, Couchbase, and other solutions. But in the end, what the store does is not the whole story. Because the surface of the store is actually hidden by your application. And what's really important is what the heck is happening inside your application. So why does everything work? Well, we've seen a number of issues, a number of weird things, and your application may actually never have a problem using an ACID database or using a mostly available database but still expecting it to give you consistency. Well, maybe during your course of operation, you did not experience a partition. Or maybe you just simply don't have enough concurrency. And so, just like the Java memory model can be nice with you under light load, you may have the exact same effect in your application. What's true as well is that you may actually gain higher consistency semantics by the way your application interacts with these solutions, because your application code has checks, retries, a number of things that can give you a better, from the user's perspective, a better guarantee than the sum of all its parts. Or simply, you've got a good first and second line support. And they get tickets that data is inconsistent, they have to fix it, and probably issue some kind of update bill to the customer or stuff like that. So what should you do then in your application? Well, your application probably cares about neither of the ACID or the CAP theorem consistency. Your application should have its own set of rules, and it's with regards to those that it needs to be consistent. And so, when you're composing systems, you really need to be aware that these multiple pieces, that storage system, that eventing bus, a messaging layer, a number of services built on top of that, whether they're distributed or not, a set of UIs, I mean, web applications, mobile applications. There is a huge difference in terms of latency, partition, opportunity between what happens in your internal network and what happens on a consumer phone. And so it's really important to understand and grasp all that context in order to be able to do something. And I think it's also something that library should provide you. For example, we've tried something with the new version of Ehcache, still under development, but the proposition is that the cache should never be the cause of an application error. After all, returning null on a get from a cache is perfectly valid. It just means the cache doesn't know about the mapping. So what we said was that, well, for in-memory, it's pretty easy. The cache should always be consistent. I mean, if we fail at that, then we fail the basic premise of the cache of being thread safe and supporting concurrent access. But if you go to a write-through pattern where you want the cache to be the one delegating the rights to the database in order to simplify the way your application interacts with the cache and the data store, and it gives you also potentially stronger guarantees, well, when that fails, we obviously don't want the entry to be in the cache. Otherwise, the cache is hiding that failure. So what at least should happen is that the entry should disappear. But then also, potentially, you may want your application to be warned that the write didn't work. And when you move to write behind, adding asynchronicity, it becomes even more complicated because the entry is in the cache, while the mapping did not make it to, the update did not make it to the database. So you create, just the fact that you ask for asynchronous, which gives you performance improvements potentially, but just the fact that you ask for it gives you an inconsistency window. And what happens if indeed the update in the database actually fails? But if you move to distributed, like with a distributed cache, it becomes even worse. And here, the idea we have is that we need you to tell Ehcache what to do. There is no way around that. What happens if we can't guarantee that the entry has been invalidated on the other nodes? Is there something that your application can do about that? Maybe not. Maybe it just crashes the user thread and the user believes his change never made it in, which actually may also be false because it could have made it in. So really, in that whole scheme, I think you really want to analyze the properties of the system. And the system is, of course, your application, but it's also the tools it is built upon. And don't stop at the marketing. Go read like the results of Jaspen test, show how these systems break, because that's what you need to know. And then you can decide, I know it will never break like that in my data center because X, Y, Z. Or, oh, okay, I understand the kind of breakage, and I know how to work around it from the application level. So once you've got that understanding, we can also guess the consequences. And that's when you can finally really make an educated decision on what to do and how to minimize these impacts. I've mentioned them a few times, but so Afir and all things Jaspen, it's a great reference as soon as you're interested in the NoSQL and NewSQL space. I cannot recommend watching his blog and conferences and Google Hangouts he publishes and stuff. It's really, really interesting. Peter Baylis, who was a graduate student and is now a researcher in universities in the US, has also a very interesting blogs and usually publishes all his paper freely available. So that's a great source of information for that space. Adrien Collier has a blog entitled The Morning Paper, where he talks about research, like trying to help understand the paper every weekday, actually. So there is quite a lot. But it's varied topics, so if you have a topic of interest, you can focus on it. So that's also another one. And of course, much more. And I think, really don't forget, build on the shoulder of giants, but please look at the giant. Thank you. Any questions? Sorry. That one? That I can do, no problem. Any other question? OK, thank you for your time. I hope you enjoyed it.